Welcome back to the classroom. My name is Mr. Wong. Today we'll be explaining the 2020 HSC Physics paper, question 22. This question relates to Module 7, Inquiry question 3 and 4. So let's get started and let's try and solve the question. So it says that a capsule traveling at 1200 or 12,900 meters per second enters Earth's atmosphere, causing it to rapidly slow down to 400 meters per second. During this re-entry, the capsule reaches a temperature of 3,200 Kelvin. What is the peak wavelength of light that's emitted? So for this question, we are using Wend's law. So Wend's law states that the peak wavelength that appears is related to the constant B divided by the temperature, absolute temperature that we have, in this case 3,200. Okay, so you can find the value for B, that's on your formula sheet. So that is 2.898 times 10 to the power 3 divided by our temperature of 3,200. So plug that into your calculator and see what value you get there. And so we get a value of 9.0562 10 to the power of minus 7 meters. So that's within the infrared spectra, I do believe. So that's the value that we get here of the peak wavelength. Question 2, it says outline two limitations. So we need to firstly outline. I might just highlight it. So we need outline, and then we need to talk about two limitations applying special relativity to the analysis of the capsule. So special relativity, firstly, special relativity cannot be applied here. Now the first reason, and I'll change colors, the first reason being is we have an acceleration, right? So acceleration doesn't work because special relativity is applied for non-accelerating bodies. Or what we could say is a inertial frame of reference. Okay, so because there is acceleration, special relativity only applies for inertial frames of reference, so constant velocity. So hence why it can't work here. The second factor is the low speed. Okay, so a low speed. If we actually look at the Lorentz factor, you will actually see that it's a really small value. So low speed, hence relativistic effects would be small. if object was traveling at a constant speed? Just to put that in reference, the Lorentz factor is this equation here, v squared over c squared. So at that point, at the very starting point, if we have a very low value, so this value kind of down here, the Lorentz factor is virtually nothing. So it's very small, and so that explains why we wouldn't really see any relativistic effects. Okay, so it might just be an ending quote. So that would be the reason we have there. Okay, so that concludes this exam explain section here. Hopefully you've found a better understanding of Einstein's application of special relativity and also a better gauge of Wien's law. Mr. Wong here, have a nice day and keep enjoying these videos.